All right, welcome back. Let's get started. Today we're going to be jumping around quite a bit. It's a bit of a catch up day for us, but that's okay. There's a lot of good things to cover. So my three goals today would be: I want us to cover the SIMD extensions for MIPS. It's a bit of a side topic, but because certainly we've asked homework questions about it, there's bonus point criteria on the current assignment in lab for it. I want to make sure we spend at least some time on that in lab. That'll be the first thing today. Then we're going to have our quiz. So people who come in late, wait about 10, 15 minutes and we will have our quiz. And it's a very straightforward one. And then I'd like us to finish up the ALU design topic and looking at some slightly more advanced designs for different ALUs. So we'll try to keep on schedule today because there's a lot we do need to cover. So backing up a little bit, and this is actually backing up quite a bit to lecture number 3, which is ancient history. We all know, and in lecture number 3, what we had been doing was looking at one second here, looking at just for loops in MIPS and trying to understand different ways in which we can improve upon that encoding of that for loop. One such approach was just looking at the branches and recognizing that branches, beyond just being conventional instructions, are maybe potentially expensive instructions. I've lost my controls here. Here we go. Okay, there are potentially expensive instructions, and so if we have a straightforward for loop like the following, which is just iterating 32 times and incrementing a value based on an array we index, we could see that potentially there's a lot of instructions happening here. We talked briefly at the time, and we've brought it up again since then, about the difference between static instructions and dynamic instructions, where the static instruction count is just how many bytes or how many instructions we have to store in our instruction memory for the code. The size of my executable is our static instruction count. Whereas our dynamic instruction count is how many instructions will it take to execute this entire code. And some people have said, well, for this code base, I don't know the answer because it's got an input n and we don't know what n is. Well, we can then typically answer the question in terms of that n. And it relates to that complexity analysis you would do in an algorithms class. It's directly related to it. The difference being that when we're either simulating or executing code, we tend to be able to measure it directly. We can say exactly how many instructions this code requires. It's a knowable quantity. Generally, at compile time, you can know a lot about what the dynamic instruction count would be, and then certainly at runtime, you can directly measure what the dynamic instruction count would be. So again, this is going way back to lecture number 3, but just looking at a very basic for loop, one such optimization we briefly talked about was a compiler optimization referred to as loop unrolling, where in our loop unrolling, we're replacing the body of that loop with multiple copies of the body of that same loop. It looks very similar. The difference is we're not iterating as many times through that loop because each time through that loop, we're basically doing 4x the work. We're doing what would have been 4 iterations of that loop body each time through. In terms of static instruction counts, originally it was 10 instructions, and counting this out isn't necessary today, and now it's 19 instructions. So by doing the loop unrolling, our code has gotten larger in terms of static instruction count, but our dynamic instruction count should have improved. We're doing mostly the same work, right? Ultimately, you're still reading from array B and adding it to J and storing the result as array of I. That doesn't change. So fundamentally, it's doing the same amount of work, but we're able to do it in fewer instructions with this loop unrolled version of the code. Very fewer instructions because we've gotten rid of a number of those branches and a 4x number of those branches because we're just branching less. We're going through the code 4 times each time through the loop. We need 1/4 as many branches. And at the time when we brought up this topic, I said, well, this is annoying enough. We're struggling enough collectively as a class on this topic. Let's skip over this. And now I want us to go back to it, which is a different type of philosophy for how we can get parallelism out of our computer architecture. And this would have significantly less control overhead even than the loop unrolled example, and would have a very nice trade-off in terms of static instruction count versus dynamic instruction count. And MIPS, as well as almost all ISAs, has kind of the scalar ISA or the general ISA or the vanilla ISA, and then there are a number of different extensions to that ISA. So it's all part of the ISA. I have to be a little careful. I'm not referring to it as this completely foreign thing. But typically, a processor can be categorized by what subsets of ISAs does it support. And for MIPS so far, we've just been supporting MIPS, and we've just been calling it the MIPS 32 ISA, and that is correct and that is true. But what I'm saying is that MIPS, like almost all other ISAs, also has these defined extensions. MIPS refers to them as application-specific extensions, and they refer to this one as their DSP, or their digital signal processing extensions. The naming for these extensions are, half marketing and half technical. There's nothing really specifically digital signal processing about these extensions, but they're a way of extracting parallelism out. And the philosophy that they follow, and many ISA extensions look quite similar for this reason, is referred to as SIMD. Now, with all acronyms, I never know. Do I spell it out? Do I pronounce it? This one I know for a fact that you pronounce. It's not SIMD. If you call it that, no one's going to laugh at you. But referred to as SIMD, and it's a form of so-called sub-word parallelism. And I want us to talk about that a little bit. And I'm just gonna write that out as our background here. That we are looking at SIMD, single instruction, multiple data. It's actually a pretty nice acronym, because it's exactly what it's describing. That the type of parallelism we're going to get out of this class of instructions is going to use a single instruction to process multiple pieces of data at the same time. Other terms that are very closely related, and it's a bit subtle what the differences really are, and not super relevant for us, but you may hear about other architectures or other extensions that are vector processors. It's an extremely comparable concept. Vector processors are instructions that operate on vectors of data at a time. And that's basically what we're doing with this as well. You may also hear the term, this is also partially marketing, is NVIDIA likes to use the term single instruction, multiple thread, really trying to get the point across that there's multiple threads of instructions that are all in parallel operating on multiple data. It's really a very similar idea. So if you see SIMT, SIMT, or vector processors, it's all basically referring to that same concept. And the main concept behind it is that, again, inside a single instruction, where for the ISA we're learning so far, we're just operating on a single value at a time, and it's a 32-bit value. It's whatever's in that register, we're adding it to another register, and we're storing the result. Instead of doing that, have a special way of interpreting the values in those registers as being multiple values that we could then operate on concurrently. And at least from a source code perspective, it would look like this. And like all the examples that showcase SIMD instructions, they tend to look so artificial because the real code in real world SIMD is extremely messy looking. So we, just like in the homework question, we try to simplify it as much as possible so it's actually somewhat tractable to do that mapping. But so what this code is doing is it's using a couple of those SIMD DSP instructions for MIPS, of which there's two of them shown in this example here. So the first one is repl v, so replicate a value. And if we look at the specification for the MIPS SIMD instructions here, they all kind of look like that. They have a mnemonic, a name associated with them, and then just a way of specifying that this is an extension, a .qb value here, and that QB stands for quad byte. So what this instruction is doing is it's taking the value J, which was already stored in S1, it's taking the least significant 8 bits of that J, and it's replicating it across all four quad byte, all 4 bytes within that word for that register S1 here. We do have a guide or a quick guide on Canvas with regards to an equivalent of the green card. No code yet. We're getting there. With regards to the green sheet we have for the conventional instructions, we also have a version of that for the SIMD instructions. I've mentioned in the past that the green sheet's kind of hard to read. You have to really, you look at all the footnotes, you have to understand the shorthand conventions that are being used to describe what's happening. This one's quite a bit worse in my opinion. It's just, there's a lot going on that you have to unravel to appreciate what is happening here. At least for this class, we're only really focusing, to the extent we're focusing at all, on the SIMD extension instructions that are doing integer arithmetic on that quad byte data. So we could look at, for example, this first one, which is the first one we're using. So replicate has a destination register and a source register. And then those are still just 32-bit registers like they would be the regular ones that you've already implemented in your register file. And the destination register is going to be the least significant byte of the source register. And that's sort of a replication or concatenation copied 4 times. And you may think, well, that's kind of a weird thing to do. Why am I ever doing that? And if we go back to the code, you can see where the advantage would be there. If we take that value of j, and again, j is part of our for loop, right? Each time through the loop, we are adding the value j to that input value b of I. So as we go through the loop, we first start off and we replicate that value j so that there's now basically 4 copies of j stored within that same register. We can still do the same load word and store word as we were doing before. From the memory's perspective, whether it's a 32-bit value that represents a 32-bit data value, or whether it's a 32-bit value that represents 4 8-bit values, from the memory's perspective, it doesn't really know, and it doesn't really care. So we can use that same exact load word instruction. There doesn't need to be a load word.quad byte extension instruction at all, because we're just loading 32 bits from memory for that instruction. So just like the original version of the code, we're still doing a load word here. We're loading that value into a register. And now instead of iterating 4 times and doing those 4 adds, we actually can just use another one of those SIMD instructions, and that's really the whole point here. We have, instead of an addu, it's an addu.quadbyte, which is doing something very similar to our existing add, but it is adding not just T1 and S1 as 32-bit quantities. Instead, it is adding them as individual 8-bit quantities independently from each other. And then we store the result back. The nice thing about it is we're able to iterate significantly fewer times through the loop. This takes even half the number of instructions as the previous version with the unrolled loop would do. We can look at that addu example here. Addu.quadbyte is this second entry that we have here. Again, it looks in terms of the register inputs to it very similar. RD, RS, RT. This is completely opaque in terms of what this is trying to say. Let me unravel it for you here. RS subset XY plus RT subset XY, where XY is in the set LL, LR, RL, and RR. Well, we have to go back to our key, our guide up at the top. That LL, LR, RL, and RR are referring to the 4 bytes from left to right inside that register. So take the most significant byte and add them together. And then take the next most significant byte and add them together. And do all 4 of those bytes independently from each other. Again, this only works, that's in theory 4x parallelism, right? Where for a single instruction, we've done 4 additions now with that addu.qb instruction here. So in theory, we're getting a 4x speed up. It only works if our program has a need to do 8-bit addition, right? If our data fits into that type. If our data values are 22 bits wide, or that's the precision that we need for it, none of this is really going to work for us. Or we have to explore some accuracy and performance trade-offs of our code and try to shrink data down to get it to fit into this format. But for code that is effectively just 8-bit arithmetic, then these are pretty powerful instructions because they're allowing you to do 4 things for every given instruction. And now coming back to what that means from an ALU perspective, we could start to think about how we would go about implementing those instructions. So using them is just something you have to kind of play around with. I don't think there's any shortcut to that other than that we have a version of the Mars simulator that has several of those instructions implemented. And if you use that version of it, they should assemble and they should simulate for you. And that was what you would want to use for your homework. There's no harm in using that version of the simulator on Canvas as your default MIPS. It doesn't break anything of the old version of MIPS. It just adds those new instructions. So let's say if we wanted to implement that first instruction, the replicate instruction. So replicate value on a quad byte level. Again, in terms of inputs, it looks pretty simple. Has some destination register, which is kind of irrelevant from our implementation's perspective, but it has an input source value. So it takes as input what is ostensibly a 32-bit value, has an output that's a 32-bit value. In terms of implementing this, this should start to look like something we can actually implement in our existing ALU. And that's the other advantage of this SIMD mode of operation. It does not necessarily require a clean slate redesign of your ALU. Via just relatively small tweaks of the existing ALU or just controlling the input to your existing ALU, you may be able to potentially implement these instructions with very minimal overhead overall. Well, how would we do this one? We already have our ALU that you've built or you're in the process of building that has inputs IA and IB. And these are already 32-bit inputs. And those are the values coming straight from the register file. Or, there's also an I-type version of this instruction. We're getting to it. IA and IB, those 32-bit values as inputs to my ALU. And again, IB, I guess, could be from the register. It could also be the immediate type if there's the REPL I or whatever the constant version of this is a very similar instruction here. And the idea, if we were to look at our way of kind of interpreting the RTL or the pseudocode for that instruction, this instruction is storing as a value of T1 or my output F of my ALU. It's only looking at the least significant bits, the least significant byte of T0. And I think if I hadn't just shown and brought back that example from lecture 3, it'd be very much fair game then to ask, well, why would we ever need to do that? Well, that's the answer. If we have a value that it's basically adding a constant or multiplying a constant or doing something that's a constant, and we want to now use that constant for these SIMD instructions, this would be the instruction we'd want to use for that. So that's really the only use case for it. Otherwise, this is not an operation that typically corresponds to math that we want to do, right? Why do we typically want to take the least significant byte and then copy it 3 times into making a 32-bit value? But that's exactly what this would be used for, that for follow-on instructions that now want to use that constant value or that value that was in the register multiple times in one instruction, this gives us that parallel version of that implementation. So in terms of implementing this, well, let's think about what we would do. Well, first off, IB isn't needed at all for this instruction, right? It has just one source register and then the destination register. So we can kind of not disconnect, but in terms of our muxes, we don't really care what the value is of IB. We have our existing adder implementation, but in terms of what we'd actually be doing for this, it'd be no more difficult than just taking those values and truncating those upper 24 bits. And calling that result, output output F, output C, whatever you want to call that output. We could also, if we wanted to, because right now this would require some sort of full 32-bit mux to implement this, we could also now, having split that input into the individual 1-byte quantities here, we could actually connect it up to our full ALU now, if we wanted to. And I'll show it just being bit by bit here. We could connect this up to the first 8 bits of our ALU and just make sure we're adding 0 to it, and do the same for each. It's kind of 6 of one, half dozen of the other, right? If you're adding a constant, you're not really engaging any of that logic that's inside the adder anyway. But this allows you to implement it without really touching the rest of your design. I'm missing one. 1, 2. There we go. And then that would then be our 32-bit output. F or C or whatever we want to call it. Yeah, and in our implementation, at least so far, all of our adders are basically 1-bit adders, right? Anyway, right, with our ripple carry design. So it doesn't really matter since we're adding 0. You can think of it as a single 32-bit adder or individual bit adders. I just drew it as 8-bit adders here because we can kind of group the hierarchy logically to draw it relatively simply there. That'd be one way to do it. You could also then, with this instruction, just treat it as another mux input, right? We have another mux input, and we are um, selecting this as the input to that mux if it's this particular instruction. Before we jump to the quiz, let's do one more example of how we would implement an instruction here. Sure. I'm hearing from people today. This is great. Yeah, and you're right. As I was mentioning, either way is fine, right? If we want to just do the concatenation operation, we need another input to our kind of big mux at the end of our ALU, and we need to select that as the output of our ALU. Versus either approach is fine, mind you. Versus we already have this, right? You've already built this for project part A, or for your regular integer ALU. And so this would be one way to engage that ALU without having to really change very much. You're just changing the input to the ALU at that point. It's a sixth of one, half dozen the other. They're both perfectly valid approaches. If we were to look at the add u.quad byte instruction, again, at first glance, that's extremely similar. In terms of the inputs for it, right? It should be very similar to the regular add u instruction, T1, T2, T3. Whereas with a regular add instruction, or add u instruction, we can visualize this as just being a single adder that we're implementing here, right? Where an input value T1 is coming in, input value T2 is coming in, and we are adding them together. Those 32-bit values. And getting some output that we're then storing as T3. That's our regular add instruction. And the add u.quad byte, again, if we go back to our green card-like reference sheet, is very similar. Well, you have to kind of interpret what it's trying to say here. First off, it's treating the values as unsigned data. That's what that little theta symbol or null symbol is representing up there. Treat it as an unsigned operand, and then do each byte of the addition independently of each other. So in terms of what that means from like kind of a logic breakout perspective, that actually then looks quite a bit different, right? Now we would have T1 where T1 it's still a 32-bit value. That doesn't change. Okay, let's try this again. That doesn't change. And same for T2. I hope so. We'll find out. So we have T1 and T2. And if I get it wrong, we'll find out, and I'll just do it again. You won't even notice that it was a completely separate recording. You won't even be able to tell the difference. I won't be at all just terribly depressed during that second repeat recording. It's still 32-bit values. We're still adding them together. But if we were to visualize the additions that are happening for this case, it wouldn't actually be a single 32-bit addition anymore. It would be multiple 8-bit additions happening in parallel with each other. So the most significant byte of T1 would get added to the most significant byte of T2. Same with the next most significant byte, and so forth. And then that result then becomes our output register, our output value. In the same way that we were grabbing the bytes for our input values. And in terms of implementing that, we can think about that as well, right? So you're right that whoever asked, what's happening with regards to the replicate instruction isn't really doing any math. So to the extent we need to engage our ALU at all isn't really that clear. I gave one example in which we didn't have to engage the ALU, and one example in which we did. In this case, we probably should be using our ALU. We could build a completely separate ALU for this purpose, but we really don't need to either, right? Because we already have that ripple carry design. And I'm not going to draw all of it, obviously, but we have already our design. And I'll get to your overflow question in a second. In which we have these full adders that are rippling, are connecting from carry out of one to carry in of the other. And that already allows us to support our conventional 32-bit addition, right? What if we were to want to also now support this independent 8-bit additions? Well, let's think about that a little bit. Ignoring the question about overflow and things like that for now, the DSP instruction set does explicitly talk quite a bit about that. But ignoring that consideration for now, we're treating these 32-bit values. I have this kind of backwards. That's fine. We're treating those 32-bit values as 4 8-byte values that are independently being added to each other. We already have an ALU that does 32 bits of addition for us. But what's the difference ultimately between independent byte addition and just the full 32-bit addition? If we think of it from the perspective of just this ripple carry adder, the main difference is happening as we go from 1 byte of our adder to the next byte of our adder. Specifically, when we get to, if this starts at 0, at FA7 here. And not just at FA7, but also then at FA15 and FA24. Where in general, we have this carry chain that's happening in our design, where at the output of bit 7, that carry out should become the input to our bit 8 of our full adder. That's for the conventional addu instruction. But for our addu quad byte instruction, those bytes are completely independent of each other. This isn't an actual hierarchical grouping in our design, but logically we can think about this part of our 32-bit adder as being independent from the next part of that 32-bit adder. And same for the next 8 bits and the next 8 bits all the way up to our final one of 31 here. So how could we treat that? How could we deal with that issue with regards to that carry out bit? If we're doing the 8-bit additions completely independently from each other, we may still, adding a mux is always the right answer, thank you. We may still have a carry out bit. What we do with that will depend on what the instruction is specifying we do with that. But we do know that that byte of addition should be independent of the next byte of addition. That carry out from FA7 should have no impact on the carry in for FA8. So in this case, you could add a mux. The other component that would work for our purposes would be like an AND gate here. That's supposed to be an AND gate, where we would have some control input coming in saying, is this a quad byte instruction or not? And maybe it's got a little inverter or something like that. If we call it that a positive thing, that it is a quad byte instruction, we'll add a little inverter there. If it is a quad byte instruction, let's be honest, that looks terrible. If it is, let's draw this a little bit better. If it is a quad byte instruction, we can decide to ignore, and let's draw this as looking at the connection between FA7 and FA8 here. If it is a quad byte instruction, that carry in to the next bit, there we go, that is very, very slightly better. I'll say it for the final time. If it is a quad byte instruction, that carry into the next bit of addition should always be 0. No matter what's happening in that first byte of addition, that carryout should not affect what's happening in the next byte of addition. We're treating them as independent additions. Otherwise, if it's not a quad byte instruction and this value is 0, then whether there's a carry or not is a function of whether or not there's a carry out from that independent 8-bit value that we have there. Let's pause here for a moment because I don't want us to run out of time and I want us to at least get to our quiz. I will come back to this before we move on to the next topic. So uh, collect yourself a little bit. This is a very straightforward quiz that should not take us more than just a couple of minutes here. Let's go navigate to Canvas and open that up, and I'll let you know the code to do our weekly quiz. We are on week 7 of the semester, believe it or not. Wow, we are making progress. So this is quiz 6 that you want to be navigating to. And the password I will type into the Zoom chat here. So let us just take about 3 minutes to work on this, and we'll come back together. Hmm. Let's just take one more minute and finish up that quiz. Um, I don't think I need to give away the answer, but for that first question, what I want you to recognize, certainly if this comes up on an exam, is given the information provided, that's an Amdahl's law question. So you may have to reference back. I know you haven't been studying Amdahl's law in any depth, but that's a straightforward Amdahl's law question. And the second question, I would expect you to be able to reason about. Okay. So let's come back here now. We're running a little bit out of time already, which is okay. These topics take time. As I was discussing the addu.quadbyte, There was a lot of discussion about, what does overflow mean in this context now? And I think that's a very valid question to bring up because as part of this transition to SIMD instructions and these values being treated as 8-bit quantities, overflow is going to be a lot more common, right? I mean, it's fewer bits to store the information. If we're not careful as we're adding things together, we're going to be just that much more likely to overflow. And the answer is there in the data sheet, but it's pretty obfuscated in terms of what the spec is for these instructions. And there's a couple different things that are provided as an answer to that question of how we deal with overflow. Um, the first, for just the regular add u, is that little symbol here that's specifying that these are our unsigned operation here. So we don't have to worry about the project part A calculation of overflow with regards to adding it two negatives and getting a positive result back out. We treat these as 8-bit unsigned quantities to start with. So that flavor of overflow is not an issue for us. Um, so our value is between 0 and 255 that we're adding together. But we know we can still have overflow in that scenario, right? If I add 250 plus 253, I'm going to get a value too large to store in our 8 bits. We're going to carry out of that circuit, which for those unsigned operations is absolutely a type of overflow as well. Well, it does give an answer for that in terms of what the instruction does, because it says it does absolutely nothing for that. If we overflow, we just overflow. In that case, we presumably just get a wrong or truncated answer, a wraparound answer for that addition for those individual bytes that are overflowing. But I think recognizing that this is a very common concern when you're doing DSP type applications, when you're dealing with SIMD values, there's also this second instruction here, right? This add u underscore s dot qb. Um, which is very similar, right, in terms of what it's specifying for the RTL here of take each byte individually, treat them as unsigned values, and add them together, and then put them in brackets. Well, okay, now we got to go back. What does it mean to put them in brackets? And it's kind of hinted at here, where the trademark symbol means rounding, but the brackets means a saturation operation. So that would be a add u and saturated operator, and specifically an 8-bit saturation operation. Something that I guess I don't really know when you would have seen this in other classes. It's not a horribly complicated concept of saturation. The idea is when you're saturating something, it's kind of like a ceiling operation, when you're dealing with floating point values, but it's not quite rounding either. It's taking a value, and if it's going to be larger than what can be represented in that data type, instead set the value to what the largest possible value is. Set it to max int, or in this case, max unsigned byte, if the value was going to overflow, if it was going to be too large to fit into that. We can think of that as a very basic circuit that we call it like a SAT8 circuit. So 8-bit saturation circuit, which would take in an input byte and produce an output byte. And again, now this would be for the add u underscore s dot qb. For the regular add u dot qb, it doesn't do anything. Whatever gets outputted, and it's just going to be whether that's quote unquote wrong or not. Really, again, as we talked about with regards to overflow, really depends on what your goals are for that application. We can't say rightness or wrongness. It's not what our arithmetic tells us the answer should be, but whether that winds up being a wrong result depends on how we want to use it. So that with the saturating circuit, in terms of inputs and outputs, if my input is something that's well within the range, so for example, I'm providing inputs and I'm providing 1, 5, 17, etc., my output is just going to be that same input. If the value fits within the range of what the circuit should represent, of what the data type should be able to represent, then my output is also going to be that value as well. But if my input is something that's overflowing, if it's something that can't actually be represented in that 8-bit value, so if it's 300 or 3,000 or 3 million, it doesn't really matter at that point, then my output is going to be that saturated value, the maximum possible value that can be stored in that 8-bit type. there's a little bit of circular logic here. If my input is 8 bits, how am I storing 300 in? But let's assume we have an input that is meant to represent an 8-bit quantity for this circuit, and it's not. It's too large to fit inside that 8-bit quantity. The output of our saturating adder or any sort of saturation operation would be, instead of the value itself, grab the maximum possible value for that number, for that 8-bit data type. And that's actually also not too difficult of a thing to implement here. We already have our full adder that's doing the quad byte addition, so that part of the instruction does not change at all. We're still doing quad byte addition. There'd be no units for that solution for Q1. It's how much faster would you make something. So we have our individual bits of addition here that are still the case, and we're recognizing that for that output of that 8-bit adder, well, one of two things is potentially happening. Either it's a regular add UQB where if we overflow, we just don't care and we just take whatever value is and that's our output. We can kind of represent that as, here is the resulting concatenated bits corresponding to our 8-bit output for that part of the operation. That's for our regular addu instruction, or addu.qb instruction. For the saturating version of the instruction, well, if the value we're saturating fits well within that 8-bit range, we don't do anything. We shouldn't have to do anything at all. Only if there is what would have been overflow. Only if the value would have been too large, and if we're adding two 8-bit values, the worst case scenario is just a 9-bit value, right? You're never going to add two 8-bit values and generate a 40-bit value or something like that, right? The worst case scenario is 255 plus 255, which fits within 511, right? So it works out okay in that sense. So the only scenario we care about for that saturating addition for the individual bytes at a time is whether or not there was actually a final carryout. Whether or not the result actually really did need that 9th bit to be correct or not, to fit within that value. And now we're back to add a mux, which is always correct. It's never the wrong answer, but the question is always which mux and why do we need a mux? In this case, we would need a mux to then specify, do I take the value that my adder gave me for that quad byte, or do I take what? That would be one input to that mux. What would be the other input to that mux? Yeah, you may be missing a one or not. Yeah, but you're right. So 255, you got it. FF, whatever. A full byte. Our maximum possible value. If it's a regular addition, add u.qb, take that value. If it's a saturating addition, take that 255 if there's a carryout. So what else do we need to add to our circuit? And it's a very small thing to kind of control this mux properly. I like to think of it in terms of, translating maybe human spoken logic to the circuit elements we understand well. So the mux is one way to represent kind of a complex if condition. If something is true, then take this. Otherwise, take this, right? So that's always a mux. But if we need multiple things to be true, what would we want to add? Multiple things have to be true for us to take that second input, not just one thing being true. Definitely adding an AND gate. Absolutely. Two things have to be true. And if two things have to be true, I couldn't have drawn that much worse. If two things have to be true for that select line to be the case, that does sound like an AND gate. If this and this are true, then we select this value. Otherwise, we select the other value. And we've already said the one thing that needs to be true is the carryout has to be high. Okay, we've overflowed. But what's the other thing that has to be true? It's subtle. But this is not a wasted exercise, right? When you're designing your processor, you are doing this kind of logic translation to circuit over and over and over again. Yeah, I would argue that yeah, QB instruction also has to be true. I would agree with that. But that now kind of that is correct. You're absolutely correct, and I think if you had done it, it depends on how you generate your control logic, to be honest. But yes, I agree. It has to be a QB instruction. Whether or not you actually need that input or not, we'll see is a matter of opinion. Yes, is it a QB instruction, and is it a what do we would want to call that signal? Is it an saturating instruction? Some other control signal we would have to wind up generating. So this one's probably redundant because you would never have this if you don't have that. So it's up to you in your control scheme. You definitely need that separate second control signal without a doubt, right? Because you can have quad byte instructions that are not saturating instructions, but given this definition, there are no saturating instructions that aren't also quad byte instructions. So you may not need that second AND gate there, but conceptually it's the same. It works out exactly the same, in which we should take 255 only if two things happen. It was a saturating operation we requested, and the result actually is necessitating that saturation because it was larger than what could be stored in 255. Let's reserve the remainder of our time because we won't be able to get to the next topic, and just general Q&A about this. The instructions are complicated. I think certainly the data sheet for these are pretty complicated. Ultimately, in terms of implementing it, believe it or not, in my opinion, we've implemented 3 of them already. That's my opinion. This does assume positive numbers only, and that's a valid question. That's what that little symbol, I don't know what you want to call that symbol. That's what that symbol is saying. We look it up here. Unsigned operation is what, again, you have to kind of read between the lines, but that's what it's saying. So we're treating these as values between 0 and 255. That's for those 2 instructions we've just supported, addu.qb and addus.qb. We could also look at, and we didn't fully implement it. We did it most of the way, right? We showed that AND gate between FA7 and FA8. We'd also have to do that 2 more times, right? We'd have to do it between 15 and 16 and 23 and 24. Because it's the same principle that we are just cutting off the carry if it is that quad byte operation. The rest of these are a relatively straightforward application of the same concept. If we, I would ignore the ones that shift. If we look at, let's see, where are the 16-bit ones? They're on here somewhere. L and R. I'm not finding them on this page. There is a lot here. Let's see. Should be addu dot, not word, but dot half word. Well, take my word for it. It's on this sheet. But implementing, let's say, a 16-bit SIMD instruction, which would be, instead of treating the input as 4 independent bytes, treat it as 2 independent half words, would be extremely similar, right? The main difference for the 16-bit version of that same exact instruction would be, instead of having the AND gate at bit 8, bit 16, and bit 24, you would only want to engage that AND bit at bit 16. So whether that's another mux or whether that's an OR gate as an input to my AND gate, it's relatively the same thing. Likewise, an operation that seems like something we would need to do in software, absolute value for signed inputs on a quad byte level becomes a relatively straightforward thing. Absolute value is something we recognize what that is. It takes the negative representation and replace it with the positive version of that representation. We had an exam question that talked about how we do that in software, but we can do that in hardware as well, right? This isn't actually doing any math. This is taking our input on a byte by byte level, and it's checking the sign bit. So that would be a pretty easy operation, right? It would be whether that needs to engage the ALU or not is like what we were talking about for the replicate instruction. Check that sign bit. If it is 1, convert it to the 2's complement of that value and store that as my output. So if you're interested in engaging with these instructions, certainly play around with them for homework number 5. and analyze the performance benefits you can find. But as you're interested in implementing these for project part A, you shouldn't have to, start over from scratch. I do recommend kind of making a copy of what you already have working for project part A. So let's say you get all of project part A done, don't touch that code, right? Copy paste that code into a new file. Even though I said you can integrate them together, just make them separate so you don't, wind up with a broken version of your stuff that was already working, and that can be very frustrating. So copy paste that file, even though you can implement this all into a single ALU and start to play around with adding those adders or those and gates and muxes. That's ultimately all that's required to implement this. Some constants to do things like saturation and absolute value potentially, some AND gates for the new control signals that would be required, and some muxes to select between different flavors of the same type of instruction. Let's leave things here for today. I really want to get to that FPGA demo that was supposed to be last Friday, and now it's going to be next Friday again. Um, what the textbook talks about after it discusses the ripple carry adders are different type of adder designs. I get very excitable when talking about that topic, and so I'm worried that if I even start that on Friday, that'll be the entirety of the Friday, and it'll move on to Monday. Um, I'll make that a game time decision on Friday. But good luck finishing up. You have still a full week to be working on Project Part A. You should have been making pretty good progress because a lot of that is just um, mm, replicating what you already did for Lab 2 and then just adding additional inputs to it. And there is a schematic in the actual um, textbook that you can basically just follow in terms of signal for signal. Some of you I've seen have been struggling with the shifters, but I'm happy to help those who are doing it. It should be nice and clean code, but there's a million different ways to do it that are still a valid barrel shifter. So creativity is fine within reason for doing VHDL. I can provide this whiteboard. It's kind of a mess. If you want to look at the entirety of the whiteboard, it's like the entire semester kind of rolled into one. So I don't know. I mean, I don't know how useful that format is going to be. It's always there all semester, and it's always in all the videos that you can view. I can save some as individual files and share that with the class. Otherwise, you should be considering taking notes too as we're doing this, certainly live or maybe potentially after the fact. Let's leave things here for today. I look forward to seeing your progress on the labs and helping to debug some shifters. I kind of enjoy that, so that's fine. If you have something that needs debugging, please bring it to my attention or your TA's attention, and I'll see everyone on Friday.